Hi, welcome to our 31st lecture in Graduate Combinatorics. Today we'll continue discussing the topics of graphs, matrices, and eigenvalues. Last lecture, we finished with the following result. The complete bipartite graph, KAB, with A vertices in one color class and B vertices in the other, is an adjacency matrix that has this form with two block diagonals of zeros, and the off-diagonal blocks are all ones matrices, and its eigenvalues we determined last time are square root of AB and minus square root of AB, each with multiplicity 1, and 0 with multiplicity A plus B minus 2. As you recall, we first found 0 as an eigenvalue because the adjacency matrix that you see there in the picture has rank 2, and therefore by the rank nullity theorem, the eigenvalue 0 has multiplicity A plus B minus 2. And then we use the trace of the adjacency matrix and the trace of the adjacency matrix square to determine the other two eigenvalues, square root of AB and minus square root of AB. Now, with this knowledge in mind, we can talk a little bit about what are called co-spectral graphs. So let's say gamma and gamma prime are called co-spectral if when gamma and gamma prime have the same eigenvalues including multiplicities, and here we're using the adjacency matrix of adjacency matrices. And two, gamma and gamma prime are not isomorphic. Some authors like to leave the second part away out of the definition, and they call two graphs, gamma and gamma prime, are non-isomorphic co-spectral graphs. But I think it's easier to remember this way. So gamma and gamma prime are co-spectral if they have the same eigenvalues, but they're not isomorphic. And the result on the top allows us to find the first example of the smallest example of co-spectral graphs, which is the following. We take gamma as the so gamma is the disjoint union of cycle C4, which is the same thing as K22 union one single vertex, which is K1, and then the other graph is a star. Let's say gamma prime is K14, and clearly they're not. These gamma and gamma prime are not isomorphic. Because one is connected and the other one is not connected, for example. But gamma and gamma prime have the same eigenvalues. And what are the eigenvalues? Well, K14, by the result on the top, its eigenvalues are going to be square root of 4 multiplicity 1, 0 multiplicity 3, and minus square root of 4 multiplicity 1. So this is the same thing as 2 multiplicity 1, 0 multiplicity 3, and minus 2 multiplicity 1. Now here, K22 on the red graph, that has eigenvalues 2 multiplicity 1, 0 multiplicity 2, and minus 2 multiplicity 1. And K1 by itself has an eigenvalue 0 multiplicity 1. And when we take this joint union of two graphs, the spectrum of the resulting graph is the union of the spectra of the two graphs. And therefore, we get the same spectrum here, 0, 3, minus 2, 1. So studying co-spectral graphs, this is quite a large part of spectral graph theory. We'll talk about it later. But I just wanted to give you this example that there exist graphs that have the same eigenvalues but are not isomorphic. These are co-spectral graphs, and they are part of the study that can be seen as the discrete version of the problems, can you hear the shape of a drum that Marquardt studied in the 60s. Okay. Now let's obtain some more properties, connections between eigenvalues and properties of the graph. Now the first one is a simple result from linear algebra. So let's say let A be a real and symmetric matrix, symmetric n times n matrix with distinct eigenvalues. Distinct eigenvalues. Theta 1. Theta. Then the product j equals 1 to t of A minus theta j identity and equals the all zero matrix of order n. Okay, and this is it's essentially a result about the minimal polynomial of a real and symmetric matrix. But how do you prove this result? Well, the key thing is the spectral theorem that that states that the space Rn is a direct sum of eigenspaces, something of the form V1 direct sum all the way to Vt, where V1 is the eigenspace of theta 1, Vt is the eigenspace. This is one of the most important theorems in linear algebra and in spectral graph theory. And it tells you that any vector from Rn is a linear combination of a unique linear combination of eigenvectors of the matrix A. And now, if I want to prove that a certain matrix equals 0, well, I can just show that its only eigenvalues are 0 eigenvalues, and its eigenvectors come from these spaces V1, Vt, for example. So let's consider this matrix M. Let's call it M, the one that we want to prove that it's the 0 matrix. Okay. And now we take an eigenvector, so let U belong to Vj for some Vj without 0, for some j between 1 and t. Then we want to calculate mu, and what is that? That's A minus theta 1. A minus, theta j is maybe hidden in the middle here. But all these matrices, all these, this is T here, all these T matrices, A minus theta 1 identity, A minus theta 2 identity, all the way to A minus theta T identity, they commute because they're polynomials in A. And because they commute, you can, their product, it's the same as if you arrange it in any different ways. But for example, I can just swap A minus theta T identity with A minus theta J identity times U. So I bring A minus theta J identity to the right. And when it meets the U, it gives me the 0 vector, and that kills everything. So we get the 0 vector. So for any vector in any eigenspace of A, mu equals 0, and therefore that implies that M is the 0 matrix. Because you take X as a linear combination of, if you take X any vector, X is going to be a linear combination of vectors from these eigenspaces, and therefore Mx will equal 0. Just a second. So this result, it gives a very simple consequence that, so the minimal polynomial of a real and symmetric matrix is the, so let's put it, so minimal real and symmetric matrix is the monic polynomial of smallest degree monic polynomial m, guess with the real coefficients, smallest degree, such that MA equals 0. Right. And so the previous result just implies that the minimal polynomial of, let's say, A as min polynomial of x equals x minus the product of the distinct eigenvalues. Now, the next result will show a connection between the theorem in the eigenvalues of a graph and its diameter. So recall that the diameter of a graph is the largest distance between any two vertices, where the distance is the length of a shortest path between those two vertices. And now the result will prove is the following. The gamma be a connected graph with n vertices and diameter d. If t is the number of distinct eigenvalues of the adjacency matrix gamma, then the diameter d is less than or equal than t minus 1. Okay. So if we denote the graph, the diameter of the graph, let's say by diam or gamma, this is less or equal than t minus 1. So it's d and diam are the same. Okay. Okay, so how in the world could you find such a connection? Well, it has something to do with this previous result that we discussed about the minimal polynomial. So say A is the adjacency matrix of gamma. Now what do we have? We know that A minus theta 1 identity, A minus theta t identity is the 0 matrix. Okay, so what does that mean? That means that when you expand 0n is A minus this is a polynomial of degree t in A. So it's A to the power t minus, for example, what comes next is theta 1 plus theta t, A t minus 1 plus, if you want to expand it, is something of the form sum of I less than j less than t theta I theta j times A to the t minus 2 minus and so on. The last one is minus 1 to the t theta 1 theta t identity. But from here, what you observe is that AT can be written as a linear combination of AT minus 1, blah, 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 AI. Okay, so what does it mean? It means that if we consider the following space, A gamma, let's say, it's the set of all polynomials in A. Okay, so these are n by n matrices. And from the observation that AT can be written as a linear combination of AT minus 1 and so on, there are T matrices there. It follows that any matrix in AT in A gamma can be written as a linear combination of AT minus 1 AI. Actually, this space A gamma is a vector space over the field of real numbers, let's say. And what is the operation? So the scalar multiplication is you take a matrix in A gamma and you multiply it by a scalar, the way you multiply any matrix by a scalar. And the vector addition in A gamma is the usual addition of matrices. And if you have two matrices that are polynomials in A, when you add them up, you also get a matrix that is a polynomial in A, and all the other properties are satisfied. Now, in addition, in A gamma, we also have the operation of multiplication between vectors. So for us, the vectors in A gamma are these polynomials in A. And if you multiply two polynomials in A, you get another polynomial in A. And therefore, A gamma is called it's an algebra, and it's actually called the adjacency algebra of gamma. Okay. So it's a vector space, and the observation here in the bottom of the page that any matrix can be written as a linear combination of these T matrices tells us that it's finite dimensional. Its dimension is at most T, and actually the fact that the minimal polynomial of the matrix A is the one that we listed on the previous page shows that actually this is a basis. This set of AT minus 1 all the way to identity is a basis, and therefore we have that the dimension of this adjacency algebra equals T. It's the number of distinct eigenvalues. Okay. So we have this. Adjacency algebra, and we have that the dimension of this adjacency algebra equals exactly T. Now, the result that we want to prove. So our claim is that diameter D is at most T minus 1, which is the same thing as D plus 1 is less than or equal to T. Now, T is this dimension with A gamma, so we want to prove that D plus 1 is less than or equal to T. To prove that, we will find D plus 1 linearly independent matrices in A gamma. And what are these matrices? What we are going to prove is that the set A to the power T minus 1, all the way A and identity, these matrices form a linearly independent set of vectors in A gamma. So this is the claim that I will prove. Okay. So if we prove this claim, that it means that we have D plus 1 linearly independent matrices in the adjacency algebra of gamma, but the dimension of it is T, and therefore from linear algebra we know that the size of any linearly independent set must be smaller than the size of a basis, so we get D plus 1 is less than or equal to T. Okay, so how do we prove our claim? Well, let's assume that there is a linear combination. So there exist beta 0, beta 1, beta d real numbers such that beta d ad plus beta 1a plus beta 0 identity is 0, and not all beta 0, beta 1, beta d are 0. So it's a proof by contradiction. Let's assume that they are linearly dependent. Okay, now we take let J be the largest index such that beta J is non-zero. So this J could be D, but so this D, it should be capital D, I'm sorry, capital D. But this J could be D, but it could be any number between 0 and D. Okay, now if J were 0, then what does it mean? Then that means that beta 1 all the way to beta D are 0, and therefore the equation that we have here implies that beta 0 identity is 0, which would give that beta 0 is 0, which is a contradiction. So J cannot be 0. So now assume that J is in the set 1 to all the way up to D. Now, all right, we are going to get a contradiction in this case as well. How? So as follows. Take two vertices, let's say X and Y. So the D is the diameter of gamma. It's the maximum of the distance between any vertices in the graph. Let me call them now A and B. A not equal to B in V. Okay. So now take X and Y in V such that the distance between X and Y is the diameter. Okay. So let's call X X0, you have X1, XD minus 1, Y is XD, and consider an XY path, X0, X1, XD minus 1, XD, so X0 is X, XD is Y, of length D. Now, somewhere here, I have a X0, X1, let's say there is some Xj. Okay. Now I claim that the distance between X0 and Xj is J. Okay, this is clear because the fact that we have X0, Xj being a path, X0, Xj path, that implies that the distance between X0 and Xj is less or equal than the length of this path, which is J, okay? And if we had a shorter path, if the distance between X0 and Xj were less than J, then what would that mean? That would mean that I could get from X0 to Xj in fewer than J steps, and combining that with the path from Xj to Xd that has D minus J, has length D minus J, I could get a path of length strictly less than D from X to Y, which is a contradiction. So I would get the distance XY less than D contradiction. Okay. So the distance between X0 and Xj is J. Okay. So what does that mean? From the previous lecture, we know that if I do calculate a to the power j, take the matrix a to the power j, and I looked in the entry x0, xj, this counts the number of walks. This is the number of x0, xj walks of length j. And because I have at least one path there, at least one walk, I know for sure that aj, x0, xj is going to be positive. Okay. So that's the first thing. Now, at the same time, the fact that we have the distance between x0, xj being j, what does it mean? It means that there are no x0, xj walks of length less than j in gamma. And that means that if I take a and I raise it to the power, let's say L, for some L strictly less than j, and I look in the entry x0, xj, that is going to be 0 for any L less than j. Okay. So let's kind of summarize what we have. We have that aj, x0, xj is positive, and we have aj minus 1, x0, aj equals all the way to a, x0, xj. Identity in the entry x0, xj, they're all 0. Now, our linear combination was of the form, okay, 0n was beta d a d plus beta 1 a plus beta 0 identity, but that's the same thing as from the definition of j is beta j a j plus now let's just spell out beta j a j minus 1 plus beta 1a plus beta 0 identity. So we have the 0 matrix on the left, and we have it equals this matrix on the right. Now, if we look at the entry x0, xj on the left, it should be 0. What is the entry x0, xj on the right? Well, that is going to be beta j times aj x0, xj plus, similarly, beta j minus 1 times the entry x0, xj in aj minus 1 and so on. But all those entries are 0. So that implies that the only one that survives is beta j times aj x0, xj. But now what do we know about beta j? Beta j is non-zero and aj is positive. So this entry must be non-zero. But the one on the left is 0. So that gives us a contradiction that proves that these matrices are linearly independent, and therefore the number of distinct eigenvalues is greater or equal than d plus 1. Okay. So perhaps it's easier to remember the result in this form. Instead of thinking of it as an upper bound on the diameter, d is at most t minus 1, think of it as a lower bound on the number of distinct eigenvalues. The number of distinct eigenvalues is at least the diameter plus 1. The result is there are examples of graphs for which the result is sharp. So, for example, for the complete graph Kn, the diameter of Kn is 1, and T, number of distinct eigenvalues, is 2, because you have the eigenvalue n minus 1 and n minus 1. For the complete bipartite graph KAB, the diameter of KAB is 2, and the number of distinct eigenvalues is 3. And there are other examples, so we'll talk about later about such as strongly regular graphs. So this would be graphs of diameter 2, and t will be 3 regular, and then distance. There are also other special graphs called distance regular graphs that can have larger diameter, but t would equal t plus 1. Now, let's continue our study by proving the following equivalent characterization of bipartite graphs in terms of its eigenvalues. So to do that, so bipartite graphs. So let's start with the following result. It's a proposition. If gamma is a bipartite graph and theta is an eigenvalue, of its adjacency matrix, then minus theta, so theta, let's say theta non-zero, then minus theta is an eigenvalue. Let's call it the adjacency matrix of gamma A. It's an eigenvalue of A with the same multiplicity as theta. So what this says is that for bipartite graphs, the eigenvalues come in pairs. So except for the eigenvalue 0, if it exists, it doesn't always have to be an eigenvalue for a bipartite graph. Except for that, all the eigenvalues come in pairs theta minus theta, or theta is, let's say, positive, and the multiplicity of theta is the same as the multiplicity of minus theta. Okay. So let's prove this result. So if you have a bipartite graph, okay, so you have two partite sets or color classes, something like that. It doesn't have to be complete bipartite, although a complete bipartite graph is an example of a bipartite graph. And in that case, the result is true, as we saw earlier. But you have a partition of the vertex set into two parts, x and y. And if we label the vertices of the graph by putting the vertices in x first and then the vertices in y, the adjacency matrix of gamma, if we do that labeling, we can put x in front, y next. And what happens? We have this kind of block form of the matrix. And here we have a 0 matrix, 0x. Here we have a 0 matrix, say y. And here we have some matrix B. And here we have matrix B transpose. Now note that the matrix B is not a square matrix in general. As you see, it has the rows indexed by elements of x and the columns indexed by the elements of y. It's a 0-1 matrix, but it's not a square matrix in general. Okay. So now let's do the first small step to show that if theta is an eigenvalue, minus theta is an eigenvalue, and then we can worry about multiplicity. So let W be an eigenvector corresponding to theta. So what do we have? We have that A times W equals theta times W. Now, because we have our matrix A in this block form and its rows and columns are labeled by X and then labeled by Y, it makes sense to think of W as being a concatenation of two vectors. One is the one indexed by the first vertices that belong to X, and then the second one indexed by the remaining vertices that belong to Y. So let's call this first one U, and let's call the second one V. Okay. And now the equation that we have here, we can write it in block form as follows. We write 0, X, B, B transpose, 0, Y. So this is, I replace the matrix A. And now I replace the W by U and V. This equals theta times U times V. Okay, and I'll squeeze the result here. So on the right-hand side, we get theta U, theta V. Okay, and on the other side, what do we get? We get the first row, 0B meets the UV, so that gives me BV. And the second one is B transpose 0 meets UV, so I get B transpose U. Okay, and you know, these two vectors are the same. That means that BV equals theta U and B transpose U equals theta V. Okay. So you see BV equals theta U and B transpose U equals theta V. Okay. So again, A is 0, B 0, Y, and W, sorry, W is this form U and V. All right, so we have this information about these matrices and these vectors U and V, and now we would like to prove that minus theta is an eigenvector, eigenvalue. So to do that, we have to figure out an eigenvector for it. So since we're looking for minus theta, let's try. So denote W prime. Let's try something of these forms: U and minus V. Okay. So let's see, this is definitely going to be a non-zero vector because at least U and V are non-zero. Actually, both are non-zero, but so it's non-zero. And let's try to see what happens when we multiply A by W prime. Well, A, 0xB, B transpose 0y times, now it's U and a minus V. Let me put it below. So in the first part, we have B meeting minus V, so we get minus BV. And in the second part, we get B transpose U. But now minus BV from our previous result it equals theta U. BV equals theta U, so we get minus theta U over there. And B transpose U equals theta V. So you get theta V. And so you get theta times minus U and V, but maybe let's write it in a different way. We take minus theta as a common factor, and we get U and minus V. So this is the same thing as minus theta times W prime. Okay. And this proves that minus theta is an eigenvalue of A, because W prime is non-zero. Okay. Now, how do we deal with the multiplicity part? If we take, for example, W1 to be U1, V1, let's say WK, UK, VK, let's say these vectors form a basis of the eigenspace of theta. Let's say, K could be 1, but it could be larger. Okay. Then by our previous argument, the vectors W prime 1, which right here, it's U1 minus V1, UK minus VK. These are eigenvectors of minus theta. Okay. But now, because the ones on the top are a basis, they must be linearly independent. So being a basis means that they're linearly independent. And you can prove that if those vectors, because those vectors are linearly independent, the vectors here, W1 prime, blah, 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 WK prime, are linearly independent. I leave this as an exercise for you to do. Okay, you can just write down what it means to be, a linear combination of them being equal to 0 and go from there. Yeah, use the linearly independence of the vectors W1, WK. So now what does that mean? That means from here, we get that the eigenspace of minus theta has K linearly independent vectors. So the multiplicity means that the multiplicity of minus theta is at least K. But then what do we do? Well, so this implies that multiplicity of minus theta is greater or equal than multiplicity of theta. But we can repeat the argument, repeat our previous argument. Switching, starting with minus theta. And we get that the multiplicity of theta is going to be greater or equal than the multiplicity of minus theta. So from here, you get that the multiplicities are equal. So I hope that's clear. So in our argument, we started with the eigenvalue theta, some eigenvalue theta, and we proved that minus theta is an eigenvalue, and it's the multiplicity of minus theta is greater or equal than theta. And now we can do the same argument by starting with the eigenvalue minus theta, and the negative of minus theta is theta, and all our arguments are true, and they give us that the multiplicity of theta would be greater or equal than multiplicity of minus theta, so therefore they must be equal. So with that in mind, one can prove the following result. This is a theorem, and it's a spectral characterization of bipartite graphs. Sense? So let gamma be a graph with adjacency matrix eigenvalues lambda 1. The following statements are equivalent. One, the graph gamma is bipartite, two, the spectrum of gamma is symmetric with respect to 0. Meaning, again, that if you have a non-zero eigenvalue with multiplicity m, then if that eigenvalue is theta, then minus theta has eigenvalue also m. And 3, for any odd natural number L, if you look at the lambda 1 to the L plus lambda 2 plus lambda n to the L, this equals 0. Now, this is not too difficult to prove. I give the details in the notes. And again, this is a result that states the equivalence between a combinatorial property of the graph, which is being bipartite, and a linear algebraic property of it, namely that the spectrum is symmetric with respect to 0, or that the fact that for any odd natural number L, the sum of the L powers of the eigenvalues are 0.